Chapter 9, Module 1. In this module, we shall see how we can construct homology groups for any topological space X. We have seen earlier that if a space is triangulable, then on that triangulable space we can associate a sequence of homology groups called simplicial homology groups. Now, we shall generalize this idea of simplicial homology to get the idea of singular homology and see how we can construct singular homology groups to any topological space. So, we begin with the definition of standard n-simplex. A standard n-simplex is a subset of Rn plus 1. We denote it by delta n, consisting of all the points x0, x1, xn, the n plus 1 tuple, such that summation xi I equal to 0 to n is equal to 1 and all the xi's are greater than equal to 0. If K is a finite simplicial complex, then any n-simplex can be viewed as a copy of standard n-simplex delta n. Therefore, we may redefine an n-simplex as a continuous injective function from delta n, the n-simplex, the standard n-simplex to the simplicial complex K. So, the geometric carrier of K becomes a list of continuous injections from delta n to K. Now, this idea is generalized to obtain the definition of a singular n-simplex. Let us take a topological space capital X. Now, if we take any continuous function from delta n to x, then that continuous function is called a singular n-simplex. Now, let us take the collections S and X as the collection of all singular n-simplexes on the topological space X. The following are possible images of singular one-simplexes which are not simplicial one-simplexes. Now, if I look at this, that any continuous function is considered as a singular n-simplex. So, any continuous injection is once again a singular n-simplex. So, this is actually generalizing the idea of simplicial n-simplex. Now, we observe certain things. First of all, there is no need for the topological space X to be triangulable. So, we have started with any topological space and we do not need that space to be triangulable, and a singular n-simplex is not in general injective. So, such a map, that is a singular n-simplex, need not preserve the topology of delta n. That is very important, that it is not preserving the topology of delta n. Intuitively, geometric carrier of a simplicial complex K is achieved via gluing the simplexes along their boundaries. Now, we want to extend this idea of formation of geometric carrier of K, that is mod K, in singular case. So, for that, to extend this idea, we need to define boundaries of singular n-simplexes in a suitable manner. And for that purpose, we introduce certain functions. We denote those functions by di from Rn to Rn plus 1 for each I equal to 0 to n. We define the functions like this, that if I take any point in Rn, that is an n tuple x0 to xn minus 1, then di operated on that point will give a point in Rn plus 1 which inserts 0 after xi minus 1. That means, we are inserting 0 in the position just after I. Now, we observe that this di, the function di will take the n minus 1 standard n-simplex delta n minus 1 inside the n-simplex delta n. So, if we take the restriction map di restricted to delta n minus 1, then di restricted to delta n minus 1 is a function from delta n minus 1 to delta n. In what follows, we stick to the notation di for the restriction maps also. So, that means, we refer to the restriction map di restricted to delta n minus 1 by the same notation di. Also, irrespective of which n we are taking, di will stand for maps from delta n to delta n plus 1. So, if we write di from, say for example, d2 to d3, we will use the same notation di to define, or rather to refer to the map from delta 3 to delta 4 and so on. And we will understand from the notation which map we are talking about. Now, it is easy to see that di compose dj operated on x0, x1, xn will have this as the output. What do I mean by that? If I is greater than j, then 0 will be inserted in two positions. One is after xj minus 1 and the other one will be after xi minus 2. But if I is less than equal to j, then two zeros will be inserted, one in between xi minus 1 and xi and the other one between xj minus 1 xj. Now, we observe that n minus 1 face of delta n consists of points having 0 in exactly one coordinate. Therefore, di delta n minus 1 is a n minus 1 face of delta n. The boundary of delta n denoted by del delta n is given by the union of all these faces, that is d0 delta n minus 1 union d1 delta n minus 1 union etc. up to dn delta n minus 1. So, that means del delta n the boundary of delta n consists of all points in delta n with at least one coordinate as 0. So, for a singular n-simplex f from delta n to x, we get n plus 1 different n minus 1 simplexes, and the simplexes are f composed di from delta n minus 1 to x for I equal to 0 to n. So far, we have developed the required tools for construction of homology groups for a topological space X. Now, we see how we can define homology groups for a topological space without asking for its simplicial structure. Now, from the previous observations, we define singular chain groups and boundary maps. Let us suppose Cnx be the free abelian group on the set of generators Snx, where Snx is the collection of all singular n-simplexes. That means, Cnx is the collection of all Z linear combinations of singular n-simplexes. The elements of Cnx are called singular n-chains. Now, if we take n to be less than 0, then we define Cnx as the trivial group denoted by 0. Now, we define boundary homomorphism next, that for each n greater than equal to 1, we define a map delta n from Cnx to Cn minus 1x by delta n on f is equal to summation minus 1 to the power of I f composed di, where the summation is taken from I equal to 0 to n. And this f is a generator of Cnx, that is a singular n-simplex in Cnx. If n is less than equal to 0, then delta n's are taken as the trivial maps. So, for any n belonging to Z, these delta n's are group homomorphisms, and these group homomorphisms are called boundary homomorphisms. We show that for each n, delta n composed delta n plus 1 is equal to 0. It is enough to prove this result for any singular n plus 1 simplex f. Now, di composed dj is equal to dj composed di minus 1 if I is greater than j, and di composed dj is equal to dj plus 1 composed di if I is less than equal to j. So, if we start with delta n composed delta n plus 1 and operate that function on f, then we will get from the definition of boundary homomorphism that it is equal to summation j equal to 0 to n minus 1 to the power of j on summation I equal to 0 to n plus 1 minus 1 to the power of I f composed di, this whole thing composed with dj. Now, with simple calculation, we can rewrite this statement as summation j equal to 0 to n, I equal to 0 to n plus 1 minus 1 to the power I plus j f composed di composed dj. But that is equal to summation j equal to 0 to n summation I equal to 0 to j minus 1 to the power I plus j f compose di compose dj plus j equal to 0 to n summation I equal to j plus 1 to n plus 1 of the same thing. That means, we are breaking the summation into two parts. One is from I equal to 0 to j and the other one is from j plus 1 to n plus 1. Now, if we go through these expressions, these are very simple deduction from the previous step and finally obtain that summation j equal to 0 to n, summation I equal to 0 to j minus 1 to the power of I plus j of f composed di composed dj minus f composed di composed dj. So, since we are getting the same elements, that is f composed di composed dj minus f composed di composed dj, this whole thing in each term will be 0 and therefore, the whole thing will be 0. So, from this result, the following corollary can be deduced. For each n, image of delta n plus 1 is contained in kernel of delta n. Let us prove this corollary. If we take a member of image of delta n plus 1, call it f, then there exists some g such that f is equal to delta n plus 1 of g, which implies that delta n operating on f is equal to delta n composed delta n plus 1 operating on g, and that is equal to 0. Hence, that element f is in kernel of delta n. So, image of delta n plus 1 is contained in kernel of delta n. Now, we define the terms chain complex, cycles, boundaries and finally, singular homology groups exactly the same way as those defined for simplicial homology. Let us go through the definition of singular chain complex. Let us take X as a topological space. Consider the doubly infinite sequence CNX delta n of groups and boundary maps. We call this collection a singular chain complex on the topological space X, where CNX stands for the free abelian group on SNX for every n greater than equal to 0, and it is trivial if n is less than 0. Now, define for each n greater than equal to 0 the subgroup Bnx as image of delta n plus 1. As we know that delta n plus 1 is a homomorphism. So, image delta n plus 1 will be a subgroup of CNX. On the other hand, if we take ZNX for n greater than equal to 1, we define it as the subgroup kernel of delta n. Once again, since delta n is a homomorphism, kernel delta n is a subgroup of CNX. For n equal to 0, we define ZNX as C0x. Now, the elements of Z and X are called cycles or n cycles. The elements of B and X are called boundaries or n boundaries, and we define H and X as the quotient group Z and X by B and X. Now, we observe that C and X is an abelian group. So, all the subgroups are normal subgroups in C and X, and therefore, we can think of the quotient group Z and X by B and X for n greater than equal to 0. Now, if n is less than 0, then H and X is defined as the trivial group 0. We call H and X the singular homology groups. Now, we shall compute the homology groups for different topological spaces. We begin with computing homology group of a singleton and then extend the idea of this computation to get the computation of the homology groups of discrete spaces. We shall also see, or rather we shall expect, that the 0th homology group might count the number of path components of the space. So, let us start with finding the homology groups for singletons. Suppose capital X is a space containing only a point small x. Then we shall see that H and X is the group Z of integers when n equal to 0 and 0 otherwise. Let us see how we can compute this. For each n greater than equal to 0, we take the collection S and X as the functions from delta n to x, which takes all the points of delta n to the single point x belonging to capital X. So, that means there exists only one function f, that is a constant function which takes every point of delta n to x. By definition of C and X, n greater than equal to 0, it is the free abelian group generated by f, and hence it is isomorphic to the infinite cyclic group Z and trivial for all n less than 0. Now, we observe that f composed d0 is equal to f composed d1 etc. up to f composed dn, and consequently for n greater than equal to 1, we have delta nf is equal to summation I equal to 0 to n minus 1 to the power of I f composed di, and that is equal to f composed d0 if n is even, and it is 0 if n is odd. So, for each n greater than equal to 1, we have Z and X as the kernel of delta n, and that will be equal to 0 if n is even and Z if n is odd. And when n equal to 0, Z0x is C0x. Also, for each n greater than equal to 0, Bnx is the image of delta n plus 1, and that is equal to 0 if n is even, and when n is odd, we get the collection f composed d0, where f varies over the set C n plus 1x, and that means it is isomorphic to Z. Hence, for all n greater than 0, H and X is the quotient group Z and X by B and X, and that is equal to 0. that is the trivial group, but H0x is equal to C0x by B0x, which is Z by 0, the quotient group is isomorphic to Z. Consequently, we get what we wanted to prove, that H n x is Z if n equal to 0 and H n x is trivial when we take any other n. Now, this example can be generalized to any discrete space consisting of finitely many points. Suppose we take capital X as a set consisting of r many points x1, x2, xr, then we can easily prove that H n x is r copies of Z, the direct sum of r copies of Z when n equal to 0, and it is trivial otherwise. For any n greater than equal to 0, S n x is the collection of all singular n-simplexes. Now, using the fact that the continuous image of a connected space is connected and that delta n's are all connected, we have S n x consisting of set of constant functions f x 1, f x 2, etc. up to f x r. Now, each f x I takes all the points of delta n to the corresponding point x I. So, they are actually the constant functions. So, the generators of C n x are basically r many constant functions. Therefore, C n x is a free abelian group of rank r. Now, we see that f compose d 0 is equal to f compose d 1, etc. up to f compose d n for each f belonging to S n x. So, for any n greater than equal to 1, delta n f is equal to minus 1 to the power of I f compose d I summation over I equal to 0 to n, and that is equal to f compose d 0 when n is even and 0 when n is odd. Therefore, proceeding exactly as before, kernel delta n is equal to image delta n plus 1 for each n greater than equal to 1, giving all H n x equal to 0 except H 0 x. We can see that H 0 x is a free abelian group of rank r. In the previous example, we observed that the underlying space X is a disconnected space with r path components. The 0th homology group is the free abelian group whose rank is exactly the number of path components of X. So, the earlier example, the one which we have discussed first, is just a special case of this one, because a singleton set has only one path component. Now, we prove a theorem which shows how the path components are counted by homology groups. Let us take X to be a topological space which has the path components y j, where j varies over any arbitrary index set lambda. Now, for n greater than equal to 0, H n x we shall show that h n x is equal to the direct sum of h n y j, where j varies over lambda. It is given that capital X is disjoint union of yj's. Any singular n-simplex f being continuous map from the connected space delta n to X, its image must be within one path component, say yj, for some j. Hence, f is in Sn yj. In such case, any s belonging to Cnx can be expressed as s equal to summation Sj, where j is varying over lambda, and all these Sj are taken from Cnyj, so that Cnx is equal to the direct sum of Cnyj, where the sum is taken over j. The rest of the assertion follows from the fact that image of f is contained in yj. This will imply that image of f compose di is contained in yj for each singular n-simplex f and each di from delta n minus 1 to delta n. From this we get a very important corollary, that if X has m path components, then H0X is the free abelian group of rank m. How do we prove this corollary? Let us take capital X as the disjoint union of yj's. Since there are m path components, j is varying from 1 to m. Then H0x is equal to H0yj, where j is from 1 to m. This is what we are getting from the theorem that we have proved here. Now, if we look at H0yj, then that is actually the infinite cyclic group Z. So, ultimately H0x becomes isomorphic to the direct sum of m copies of Z as desired. So, we have proved that singular homology groups provide information about the path components of a topological space. In the following module, we shall show that a continuous function between topological spaces induce homomorphisms between the homology groups.